Heat. It's everywhere. It cooks our food, it warms our homes, it literally powers our world. But here's the thing about heat. It's restless. It is always on the move. And understanding how it travels, how to control it, is one of the most fundamental challenges in all of science and engineering. Today, we're going to pull back that curtain.
So, let's just jump right in with a question you've definitely experienced. You're outside on a cool day, there's a metal bench and a wooden one right next to each other. If you were to point an infrared thermometer at them, you'd see they're the exact same temperature. So why, when you sit down, does the metal one feel so much colder? The answer has nothing to do with their temperature and everything to do with how fast they can pull heat away from you. That right there is the essence of heat transfer.
So here's our game plan. First, we'll talk about the unstoppable flow of heat itself. Then, we'll break down the 3 ways it moves: conduction through solids, convection through fluids, and radiation through, well, nothing at all. After that, we'll see how they all work together. And finally, we'll talk about why this stuff really matters.
All right, let's get started. Our story really begins with a universal law, a core principle that governs everything from a cup of coffee cooling on your desk to the energy that powers the stars. Heat has one very simple rule. It's a one-way street. It always flows from something hotter to something colder, always trying to find a balance. It never ever goes the other way on its own. The entire field of heat transfer really is just about understanding, predicting, and ultimately mastering this relentless flow. Let's start with the most direct path heat can take. Imagine it's winter and you're nice and warm inside your house. How does all that precious, expensive heat get through the solid walls and escape into the cold? The answer is our first mode, conduction. Think of conduction as a molecular chain reaction, like a line of dominoes. The molecules in the hot part of an object are vibrating like crazy. They bump into their neighbors, who then start vibrating more, and they bump into their neighbors, and so on, passing that energy right down the line. That's exactly what's happening with that cold metal bench. It's a great conductor, so it pulls that heat energy away from your hand, molecule by molecule, very, very quick.
So how do we actually work with this?
Well, engineers came up with a brilliant shortcut. They realized you can think about heat flow in the exact same way you think about a simple electrical circuit. The temperature difference between hot and cold, that's your push, just like voltage. The amount of heat that's actually moving, that's your flow, just like current. And here's the key. A material's ability to stop heat is its thermal resistance, which works exactly like electrical resistance. And this brings us to a really practical takeaway. If you want to stop heat, you need a material with high thermal resistance. That is the entire job of insulation. You know the R value you see printed on insulation at the hardware store? That's it. That's just a measure of its thermal resistance. The higher the R value, the better it is at stopping conduction. Simple as that.
Now, in the real world, things are built in layers, right? Take the wall of a house. You've got your siding, some sheathing, and then the drywall on the inside. Each of those has a pretty low resistance to heat flow. But then you have that big, fluffy layer of fiberglass insulation. Its resistance is huge. And just like resistors in a circuit, you just add them all up. You can see right away that the insulation is doing almost all the work. It's the primary barrier.
Okay, but heat doesn't just move through solids. What about fluids, like air and water? That's where our second mode, convection, comes into play. If you've ever felt a chilly draft sneaking in under a door, you've felt convection.
So conduction was about energy getting passed from one molecule to its neighbor. Convection is totally different. This is about the fluid itself physically moving. A little pocket of air or water gets heated up, it actually travels to a new spot, and it carries that heat energy along with it for the ride.
And convection really comes in 2 main flavors. You've got natural convection, which just happens. Think of a radiator in a room. The air it heats becomes less dense and rises. Cooler, denser air sinks to take its place. Boom, you've got a current. Then there's forced convection. That's when we use something like a fan or the wind to give that fluid a push and really speed up the whole process.
Now, this equation might look simple, but it's hiding something incredibly clever. The rate of heat transfer, Q, depends on the surface area, A, and the temperature difference. That makes sense. But the real magic is that little h, the convection coefficient. That one number is an amazing engineering shortcut that packages up all the messy, complicated physics of the fluid flow, how fast it's moving, if it's turbulent, what its properties are, into a single useful value.
All right, on to our final and honestly most unique mode of heat transfer. This one doesn't need any molecules or any matter at all to get the job done. This is the heat you feel on your face from a bonfire, even when you're far away. It's how the sun warms the Earth through the total vacuum of space. This is radiation.
Here's the deal. Any object with a temperature above absolute zero, which is everything, is constantly emitting energy in the form of electromagnetic waves. Think of it as every object glowing with invisible light. That's thermal radiation. And because it's just waves, it doesn't need a medium to travel, which is why we feel the sun's warmth from 93 million miles away.
The equation that governs radiation has something truly extraordinary inside it. You can see the rate of heat, Q, depends on the area, A, and a constant. But look at the temperature, T. It's raised to the fourth power. This T to the fourth relationship isn't just a small detail. It has profound, massive consequences. So what does that T to the fourth really mean? Let's talk in terms of absolute temperature, Kelvin, which is what scientists use. Say you have an object at room temperature, around 300 Kelvin. Now you double its absolute temperature to 600 Kelvin, about what you'd find in a hot oven. You might think it radiates twice as much heat. Nope, it radiates 16 times more heat. It's an explosive, nonlinear relationship. This is why very hot things start to glow visibly, and it's why at really high temperatures, radiation isn't just a factor, it's the dominant player.
Okay, so we've met the three big players: conduction, convection, and radiation. But in the real world, they almost never act alone. They're always teaming up. So let's see how they work together by looking at a brilliant piece of everyday engineering.
A thermos, or a vacuum flask, is a masterclass in fighting all three modes of heat transfer. First, it attacks convection by creating a vacuum between the inner and outer walls. No air means no fluid to move heat. Second, it tackles radiation. Those shiny mirrored inner surfaces, they reflect thermal energy, keeping it from getting in or out. And finally, it deals with conduction by using a stopper made of a really good insulator. It's a three-pronged defense to keep your coffee hot for hours.
And this leads to a super critical insight. Whenever you have multiple types of heat transfer happening, one of them is almost always the bottleneck. Look at this example of a hot pipe losing heat to the outside air. The resistance to conduction through the metal wall itself is tiny. The resistance to convection of the fluid inside is also pretty small, but the resistance to convection on the outside into the still air, it's huge. It's hundreds, even thousands of times larger. That is what we call the controlling resistance. And it tells you that if you want to reduce heat loss, making the pipe wall thicker won't do much. You have to attack that big external resistance. So, understanding all this isn't just some academic exercise. Being able to manipulate these principles is absolutely fundamental to pretty much every piece of modern technology we rely on.
I mean, the ability to move heat where we want it and keep it out of where we don't is literally everywhere. It's in the design of the heat sink, cooling the processor in your laptop. It's in the insulation in your house. It's in the massive cooling towers at power plants and the intricate heat shields that keep spacecraft from burning up on reentry. It is a foundational science that truly shapes our modern world.
So, now that you know the rules of the game, let's bring it all the way back to the beginning. How would you apply these principles to design the perfect coffee mug? What materials would you use? What shape should it be? What features would you add to fight conduction, convection, and radiation? It's a simple question, but thinking it through shows you just how powerful these ideas really are.